In this video, I'm going to show Scala's map method. Map is defined on many of the collection types in Scala's class hierarchy. It's easiest to start talking about map as it's defined by the list. And so to have some data to work with, let's first create a numeric range. Numeric ranges can be defined with until. There's also a way to do it with to. If you do it with to, it will include the endpoint. So I'll take the first example and convert it to a list and assign it to a value called nums. If I have a function called f, which takes an integer and returns 2 times that integer, so f1 for instance is 2, I can pass that function to num's map method. Map is going to apply that function f to each of the elements in nums and construct a new list from the results, which is also going to be of type listInt. And it's worth noting that we have not modified the original list, so we're not relying on any mutability, which is a good thing. We didn't have to name that function. I could have just defined it as it was being passed in. And we can take that a step further. Because we're using the parameters exactly once and we're using the same order, I can just delete the parameter list and replace the reference with an underscore. So this has been an example of mapping on a function that goes from int to int, but it's not necessary that those things match. We can go from int to character or int to anything. Let's show an example of creating a tuple 2, what I call a double of. Now this is going to simply copy the input. Actually, let's define it this way so that we can get a name on it. We're going to copy the input x and then just apply, let's say, the same doubling that we've been looking at. So in this case, we see that the return type is list of the double int. If we look at this, we see that's a function that goes from int to a double int. So what we're doing is taking this list of int, which matches this, and turning it into a list of this, which matches this. So now that I've shown how map works, I can demonstrate how I got the scores data structure that I was using in the previous video. So we can do ranges on characters just as well as we can do ranges on integers. In the last example, I was showing a data structure that I was using to mean a set of test scores for 26 students. And I was just using the letters of the alphabet as the name of the students, and then pairing each name in a double with some random score from 1 to 100. So I built that with the map function. In this case, I'm only going to use the input once, so I can just use the underscore, and I'm just going to generate a random number for each one of these students. And let's assign that to a value called scores. In the previous video, I was doing things like sorting it. And just to show how we can compose these things, I could take the sorted vector of scores and extract just the scores once we've sorted it. That would be useful for figuring out the distribution of the scores or creating a histogram or something like that. Okay, so those are a few examples of map as it's defined on list. List is not the only collection that defines it. In fact, quite a few other types do. The next place to look at map, I think, would be the option monad. Let's create a couple of examples of that. So there are two forms of option, some or none. In this case, they're both option ints. And let's look at what map means as it's defined by the option. So I'm using the same function here. I could have just reused f. We're taking an integer and multiplying it by 2. In this first case, we see that we're taking the 4, applying f to it to get 8, and then rewrapping that in sum. So opt1 itself hasn't changed. And we're effectively getting this. So opt1, when mapped upon, is applying f to the argument, or to the wrapped value, I should say. Opt2 is a none. So there is no value to apply f to. So map as defined on none just returns a none. Map on a sum will apply f to the value that's wrapped in the sum. So let's motivate this a little bit more by creating a map. This is always my go-to example map. A is mapped to 1, B is mapped to 2. And remember that get will look up a value by key wrapped in option. So in this case we get sum 1. If we replace that with a key that doesn't exist, we'll get a none. So m get a map f. Let's just spell it out. Whereas m get z map times 2 returns none. So that gives us a nice way of dealing with both cases. So I can, let's say, take a string that's going to be used as the key to this map, just for consistency here. And here I don't have to worry about sum versus none. Get is going to return one or the other, and map is going to work in both cases. So we can see that the type of G is a function from string to an option int, and that's going to be well behaved regardless of whether the map contains that key. And furthermore, we can see that the times 2 has been applied correctly. It's worth mentioning that map also defines map. Here I'll just pass it the identity function. And set is worth mentioning briefly. One special consideration with set, and I've hit this bug a couple of times, is that the result is a set. And that means that if we take this times 2 example Well, actually, let's come up with a different example. Div2. Now, div2 this integer division. Note that two of the elements of set 1 have the same value. So if I take set 1 map we're actually not going to end up with one element in the result for every element in the input. And that's because the uniquing happens behind the scenes. I've made this bug a couple of times. If you want to allow duplicates, you could just convert it to a set, do something like that. And just a note on some of the theory, all of these things that implement map are known as functors. A good resource to read more about functors would be the book Learn You Haskell for Great Good. Although you have to do a little bit of translation. Languages refer to these things slightly different ways. In Haskell it's called fmap. In a lot of languages though, Perl, Python, even JavaScript, this map maps fairly well to what you'll find in those other languages.